Interference. In this video, we'll be looking at the interference of light when we have multiple sources. If two or more waves overlap or exist in the same space, they interfere with each other. The result is actually a vector sum of the two, and it's called superposition. So just briefly looking at the diagram that we've got on the screen, we've got a blue wave and a green wave. What we're going to do in each scenario is take the amplitude of each wave, add them together vectorially, and the result will be the red one. So when we have two waves in the same space and they're in phase, meaning crests are both emitted at the same time as well as troughs, at that point the waves will reinforce each other or constructively interfere. We look at this point here, we have a crest and also a crest here from the two different waves. Add those two crests together, we get one that's twice as big, and we have amplification as a result. When the waves are out of phase at some point, they annul each other or cancel out. And this is called destructive interference. If they are 180 degrees out of phase, so when one emits a crest, the other emits a trough, we can see that in the bottom diagram. So that's a crest, that's a trough. A crest plus a trough equals 0, and all the way along the wave, we have that cancellation or destructive interference. Here are another couple of examples where the solid black line and the dashed black line are interfering, and the result is the blue line. So in this top one, we've got constructive interference. We have a constant phase relationship. The wave's coherent, but it's in phase. So we've got the trough and the trough here. They add together vectorially to constructively interfere, and we get that result. In the bottom case, the waves are coherent. There is a phase relationship, but they're not in phase. And it looks like, again, they're 180 degrees out of phase. And we can see a maximum here plus a minimum here results in that 0. And so the result is 0. If it was light, we wouldn't see any light in this situation. One final example is when we've got waves that are not coherent. So we've got a blue wave and a green wave interfering, and in that space they'll add together to make the red one. Elaborating a little bit more so we can go further into depth, I consider two monochromatic sources that are in phase. So we call it source 1, source 2. Monochromatic mean they have the same frequency. In phase means they're both emitting crests and troughs at the same time. So this line here, MP, is equal distance at any point from both source 1 and source 2. So any point here is the same distance away. Now point Q is an arbitrary point away from the bisector. So along that line MP, any crests emitted from S1 will meet crests from S2 because they're the same distance away. Okay, so all along MP, you'll have that constructive interference. Now at that point Q, which could be anywhere, there's a path difference from S1 to S2. And what that means is you can see that the distance from Q to S2 is actually a little bit longer than Q to S1. So if the waves have to travel longer to get there, the crests won't necessarily be meeting crests anymore, so you won't get that constructive interference. You might actually get destructive interference. So just emphasizing that, I've drawn a line from Q to S1, and if I don't change the length of the line, you can see, well, as best I can, it's slightly longer to get to S2. All right, and you can see here, what I've done is actually put a circle centered at Q. The edge of the circle hits S. Again, this just emphasizes the fact that S2 is just that little bit further away. So when that little bit of extra distance that S2 has to travel is exactly one wavelength, then a crest from S2 will meet a crest from S1 at Q, and it will still constructively interfere. It might be easier to see here. So when that little bit of distance here is now half a wavelength, a crest from S1 will meet a trough from S2 at Q, meaning there will be destructive interference at that point. So that when that distance is a full wavelength or any multiple of, you've got constructive interference. And when it's exactly half a wavelength or a multiple of, then you get destructive interference. So looking at a situation where we've got two sources, 1 and 2, this diagram looks at both of them emitting monochromatic light that's in phase. So you can see both emit crests and troughs at the same time. So the crest is denoted by a solid line, a trough is a dotted line, and the interference that's produced is the lines that go from A to B or P to Q. Let's look at this point where the cursor is there. You can see that a crest from S1 is meeting a crest from S2, and in that situation you've got constructive interference, and then that's what gives this solid line. Alternatively, at this point here, a trough from S1 is meeting a crest from S2, and that's why we've got the dotted line of destructive interference. We've got two scenarios here. If the two waves in one of the scenarios interfered, underwent superposition because of interference, match up the result on the right hand side.